Okay, the previous discussions led us to these two conditions for finding all possible closed-loop poles from open-loop transfer functions. And if we connect all the closed-loop poles together, that will give us RootLocus. Basically, we want to find all the closed-loop poles to form the RootLocus. The magnitude condition, sometimes we call it gain condition, gives us a way to calculate the control gain after we know where the closed poles are. It is a phase condition that used more often where we need to identify all possible closed poles according to where the open loop zeros, Zi, and open loop poles are, and we use the point S0 as a test to say if we want to see that point is part of the closed loop with a control gain, then this condition must be met. Now, these two equations look very mathematical, but what I do is I'm going to use this diagram to show how we actually work out these conditions using the graphic approach. Okay, say I have an open loop system with an open loop 0 here, that's Z1. I have an open loop pole there. Okay, so these are from open loop transfer function, so they don't change. But I want to see this particular point S0. I want to check if that point there is a possible closed loop pole, i.e. if it sits on the RootLocus. So to apply the phase condition, I need to do S0 minus Z. Now graphically, in the S-plane, we have two complex numbers, even though these two sit on the real axis, but we treat them as complex numbers. Okay, so S0 minus Z1. Now remember the revision I did for the complex numbers. When you subtract two complex numbers in the S-plane or in the complex plane, what you do, you draw a line from Z towards S0. Okay, so Zi is where the open loop 0 is. Okay, so you draw a line from there towards S0. So that yellow line pointing towards S0 is your new number. That's S0 minus Z1. Now the length of that is a magnitude. The angle between the positive real axis and that yellow line is your phase angle. Okay. For the second part, if I do S0 minus P, you draw a line starting from that P1, from that open loop pole, towards S0. Again, that's my test point. Now, this yellow line there pointing towards S0 is my S0 minus P1. The angle is this, and the length of that line is the magnitude. Okay? To apply the phase condition, all the angles we do with open loop zeros will be positive. That's the first term. All the angles between this point to all the open loop poles, like phi p here, will be negative. We add all the angles together. If it's equal to minus pi, then this point here will be on the RootLocus, or will be a possible closed loop pole. Move the S0 to a different point, and then you draw again. You can apply the same way. You can just draw a line there, draw a line there, measure the two angles, or calculate the two angles if you like, and to see if they're equal to pi. That's how to apply the phase condition. Now to apply the gain condition, what you do here is actually simpler. You you work out the distance, the length or the magnitude of S0 minus 1. That's this value, the length there. If for all the distance between this point and any open loop poles, you put them on the top. And then you work out all the distance from that point to all the different open loop zeros. In my example, there's only one, but if you have two, you work out two distances. So you work out that distance, stick them in that bottom. Okay? Do a division between the two. That will give you the K value that will move the closed loop pool to that point. Okay? Provided this point is actually on the RootLocus. Okay? If it's not, then the second condition you don't need to apply. This one just there. Most of the time we use 1. But it's come from the open loop transfer function. So if open loop transfer function has a non-1 gain, then you have to put that one there. Okay, so but this part is what that is. So phase condition is to find all the possible closed loop poles, i.e. find the RootLocus. Gain condition is work out the K value for each point on the RootLocus diagram. That's how the phase and gain conditions are applied. Okay, I'm going to use some examples just to get us familiar with the process. Case number 1, we're going to look at points on the real axis. Okay, now if I have poles and zeros, the original on the real axis, but I want to see any points on the real axis belong to the RootLocus or belong to the part of the closed loop poles. Say I have a test point there. I have open loop pole there. I want to see if that point is a possible closed loop pole. Okay, I need to draw a line from open loop pole towards there. Now you can see this one actually counts nothing because this is pointing towards the positive side of the real axis. Therefore, the angle between this yellow line and real axis is 0. On the other hand, if I want to see the point on the left-hand side of that pole, then I draw a line from that open loop pole towards this. Now, this is actually pointing towards the negative side of the real axis. The angle here is pi or minus pi. Now, in this example, there are no zeros or no poles. In this example, there are no zeros and no poles. Therefore, we can see this point can't be on the RootLocus because this angle gives me a 0 angle. But my phase condition says I want a minus pi. Whereas the second case, this point will be a possible closed loop pole because this angle gives me a minus pi angle. Okay, because in this example, I only have a single pole for the open loop, so it's actually quite straightforward to look at. So on the right-hand side of this open loop pole, any point there, if you go there, you draw a line, that's 0 degrees. If you go there, you draw a line from open loop pole to there. Again, that gives you 0 degrees. 0 degree is not equal to minus pi. Okay, but any point on the left-hand side of that open loop pole, if you try this point, you draw a line there, that will give you a minus pi or positive pi. If it's there, you draw a line from open loop pole to there. Again, it will give you a minus pi in angle. So therefore, any point on the left-hand side of that open loop pole will be on the RootLocus. Okay, so that's really how, a simple example how to apply the phase condition. But in general, if I have several open loop poles and open loop zeros on the real axis, that's open loop, and if I have 3, for example, then it will divide the real axis into 4 different sections. Now, for each of these 4 sections, what you need to do to determine whether any section is part of RootLocus is count number of open loop zeros and open loop poles to the right hand side of that section. If that total number is an odd number, then this section is on the RootLocus. If the number is an even number, then this section is not on the RootLocus. Now, to make that point clear, I have an example here. Okay. The open loop system have 2 zeros, 1 here, 1 there, have 5 poles. There's 1 pole here, 1 pole there. There's 1 pole, there are 2 poles there as well, but they are same values, so they are actually sits on the same spot. This is another open loop pole, that's another open loop pole. Now, if I want to determine these open loop poles and zeros have divided the real axis into several sections. There's 1 section here. There's 1 section between P1 and P2. There's 1 section between P2 and Z1. And then there's 1 section between Z1 and P2, P3. P2, P3 are the same. They are 2 poles. And then there's another section between Z2 to P2 and P3. A section between P5 to Z2. A section between P5 and P6. And then on the left-hand side of P6, that's another section. So there are 1, 2, 3, 4, 5, 6, 7, 8 sections. I want to see individually each of these sections will be on the RootLocus or not. So I will start from very right. So if there's a point there I want to see, any point there, okay, look at towards your right hand side. Just from there, from wherever you're pointing, look at from the right hand side. We got no open loop poles or open loop zeros. 0 is considered as an even number. Therefore, any point on the right hand side of P1 cannot possibly be the closest pole, i.e. they are not on the RootLocus. If I move into the section between P1 and P2, and at any point there, if I look towards my right hand side, I only see P1. So there's only 1 open loop pole. 1 is an odd number. Therefore, any point between P1 and P2 will be part of RootLocus, i.e. are possible closed poles. Move between P2 and Z1. Again, look towards your right hand side. I have P1 and P2, 2 poles, no zeros towards the right hand side of any point on this section. So that's even number. Even number is not on the RootLocus. Moving towards this side, between Z1 and P2, P3. Now look towards the right hand side, I have 1 open loop 0, 2 open loop poles. Add them together, that gives me 3. So that section is on RootLocus. Move further. Now, this time, you have to be a little bit careful because I have 1 pole here, 1 pole there, 1 0 there, 2 poles there. So these are 2 poles count twice. So 1, 2, 3, 4, 5. That's an odd number. So this section will be the part of RootLocus. Go further, you get 1 more there, that's 6. So 1, 2, 3, 4, 5, 6. So that section is not. Go there, you get 7. So 1, 2, 3, 4, 5, 6, 7. So this section is on the RootLocus because the total number is an odd number. Go on the left hand side of P6. If you look towards the right hand side, you get 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 open loop poles or zeros. So that gives me an even number. So therefore, this any points on the left-hand side of P6 on the real axis can't be possible closed pole. Therefore, they are not on the RootLocus. So for this case, only this section, these two sections, and this section, these 4 are possible closed pole. They are on the RootLocus. Now, we are not, in this particular case, we are not discussing anything in the complex plane, just the sections on the real axis. Okay, so it's quite straightforward to determine. If you have open loop zeros, open loop poles on the real axis, this is what you do. You just go to that section, count number of open loop poles and open loop zero towards the right-hand side of that section. If it's odd number, then this section, every single point on that section will be part of RootLocus. If the number of open loop poles and the zeros to the right-hand side of a section there is an even number, then every single point in that section cannot be a possible closed pole or cannot be part of RootLocus. So the rule here for this particular case is straightforward. Just we can all count, we all know what even number, odd numbers are, so it's quite easy to make a decision. So that's case number 1. That's how we apply. Now case number 2. Now I'm going to look beyond the real axis only. Okay. Now in this case, I have 2 open loop poles, no zeros. Okay. There are no open loop zeros. Only 2 open loop poles. One is at minus a, the other one is at minus b, because my transfer function is s plus a, s plus b. If we equate the denominator terms to 0, and the solution would be minus a and minus b. So these will be my open loop poles. So I have open loop pole here, I have open loop pole there. Now if I apply the previous rule, I can see this middle section is a possible, it is on the RootLocus, because any point on this section will only have this pole to the right-hand side of that section. That's 1, which is an odd number. This section, you will have 2 poles to the right-hand side. That's an even number, so this section can't be. This section, you have no open loop poles or zeros to the right-hand side, therefore it's an even number. Therefore, this part is not an open loop, is not on the RootLocus either. Now, so think about very early discussions for the RootLocus diagram. We said the closed loop poles will start from open loop poles, moving towards open loop zeros. Now, in this case, they don't have any open loop zeros, therefore they're going to move towards infinite. But if you think about how they start to move as I increase the k value, this pole, it's a single pole here, got nowhere, because we know this section is on RootLocus, this section is not. So this pole for the closed loop can't move towards the right, because we know that is not part of RootLocus. It can't move to the complex plane yet, because there's only 1. Complex come in pairs, they have to have 2. Okay, so this pole will start from here for the closed loop, but move to, the only way for it to go is moving towards the left-hand side. For this pole, it's the same argument. It can't move towards the left-hand side, because the left-hand side we know is not on the RootLocus. So the closed loop pole will start from here, moving towards the right-hand side as we increase k value. Okay. Now, this towards left, this towards right, somehow they're going to meet. Okay. When they get together, they have, if you increase the k value even further, then they have to find somewhere to go. They can't go back, because they have to go find somewhere to go and towards infinite. So what will happen is that they will, when they meet each other, they will break off, one up, one down. Okay? One up and one down, that, but we need to know how it's going to go up or go down. To find how beyond the real axis, and we need to apply the phase conditions again. Okay, so I'm going to move on a little bit. So I know the section between the two poles are on the RootLocus, but I'm going to try a point in the complex plane. I'm going to try this. Okay, I'm going to try it and to see if that point is a part of RootLocus and under what conditions. Okay, so this is my test point. So now, according to my phase condition, I need to draw a line between this open loop pole towards the test point. I need to draw a line from this second open loop pole towards there. Okay? Now there are no open loop zeros, so I don't need to draw any further lines. Now the angles formed from this will give me a phi 1 with this pole, and I get phi 2, that's my second angle, that's between, for the second pole. So it's between this line and the real axis, it's between this line and the real axis. Okay? Now, because there are poles, because it's the angle between this point and open the poles, so we need to put a negative to the front. Zeros will be positive, poles will be negative. Okay? So add them together, I have a minus phi 1 add to minus phi 2. This must be equal to minus pi. If that S0 is a possible closed pole or is on the RootLocus. Okay, so we have this relationship here. Minus phi 1 minus phi 2 equals to minus pi. If we can find any point in the S-plane that meets that condition, then those points will be a possible closed poles or they are part of RootLocus. Okay, so we need to find these conditions. Now, I'm going to look at the relationship between this angle and that angle inside, on the other side of that line here. So if you look at it, this angle plus that angle equals to 180 degrees. Or phi 2 equals to 180 degrees minus theta, or pi minus theta. So I'm going to replace phi 2 by pi minus theta. That gives me the equation number 2. This pi cancel that pi out, they're both negative. This negative and minus another negative, that gives me a positive theta. This is negative theta 1, phi 1. Therefore, I end up with equation number 3. Phi 1 must equal to theta. If this point is a possible closed loop pole or is on the RootLocus, then this angle must be equal to that angle. Now, think about that triangle here. What triangle does that give us? Two sides, this angle equal to that sine angle, or means that length equal to that length. That's our isosceles. Now if I draw a line, a vertical line there, any point on that vertical line, halfway between this pole and that pole, will give me this angle and that angle the same. Will give me an isosceles triangle. So the vertical line, just to summarize, the vertical line between the two open loop poles, halfway between two open loop poles, will be on the RootLocus because they meet that condition, phi 1 equals to theta. So this is how you end up with all the possible closed poles, i.e., the entire root locus for this particular system. The transfer function is given here with two real open loop poles. This is what happens. This is where the open loop poles are, the two. The closed loop pole, as you increase k value, the closed pole will start from here, the same as open loop pole. They move towards each other. Notice I have some little arrows here, just pointing in the direction of the movement. So this one, this closed loop pole will move towards right hand side. This will move towards the left hand side. They meet right in the middle. Then they break off, follow that vertical line. One goes up, one goes down, because any point on that vertical line will give me an isosceles triangle. That's what the condition that I derive from the first condition. I must have the point that forms isosceles triangle. That position, to calculate that position in the middle, is you add the two poles together, divide by 2, so that's one in the middle. Okay? So just put some numbers in here. Now, I just replaced the A and B with two numbers. One is 6, one is -2. Now, in this case, I have two open loop poles. One is 2, one is -6. And the system is, of course, in the open loop, the system is unstable. Okay? Because the one pole actually sits on the right-hand side of the complex imaginary axis. That makes the system unstable. But the aim is to actually find a solution to stabilize, to make the system stable, and find the possible control gains. So we need to introduce feedback, but first of all, we need to find all possible closed loop poles, i.e., we need to find the root locus. And from our discussion just earlier, that we know sits in between the two real axes, two open loop poles, and we know this section is on the locus side, on the root locus, and we know there's a vertical line that also on the locus. That vertical line is halfway between the two. To work out that position, we add the two poles together. It's -6 and 2. -6 plus 2, that gives me -4. -4 divided by 2, that gives me -2. So this line actually is at -2 points. So we draw a vertical line, and now we know from the previous discussion, we know as you increase the k, the closed loop poles will start from here and there. This one moves towards the right hand side, this one towards the left hand side. They meet at -2 point. Then one move along that vertical line will move up, the other one moves down. That's the entire root locus diagram. Now, to make it clear, to get the full mark, you need to tell me not only the regions or the lines. I need to see the direction of the movement. So this one, there's the arrow pointing left, there's arrow pointing right, this is arrow pointing up, there's arrow pointing down. But I also need to know specifically at what point they break off. So you really need to mark everything down in the S-plane to make it absolutely clear. Okay, so that will give us the answer to part 1 that says sketch the root locus diagram of the closed loop system. And then the second part is that we want to find the control gain when the closed system becomes stable. Now, the entire root locus diagram is given here. So it's towards right, left, towards right, one go up, one go down. This is actually the red dotted line. You can actually go up infinitely, you can go down infinitely here. The red dotted line are the connection of all possible closed poles. Each point on the red lines, each point represents a possible closed pole, and each point corresponding to a different value of k. So we need to work out to make system stable. When the closed loop system becomes stable, is this pole. This pole moves to the right, it becomes stable when you get to the point of origin. Move any further, it will be more stable. This is where it becomes stable. So S0 is where it becomes stable. So we want to find the k value to that point. So that is my test point to work out the k value. To work out the k value, what we said is we find the distance between that to this pole, that's 2. We find the distance between this point to this open loop pole, that's 6. So stick that to the top, 2 times 6. We got no open loop 0, so there's no distance to work, so that's 1. So 22 times 6 equals to 12. So when k equals to 12, the closed loop pole will move from positive to 0. So system becomes stable. That's 12. But if we look at the part 3 of the question, we find the control gain when the unstable pole is moved to S-1. We not only, in this case, we not only want to just move to here, we want to move a bit further to give us some margin for stability. So it becomes more stable, -1 there. When you want to work out this one, so if the test point is -1, now I need to work out the distance between -1 and 2. -1 and 2, that's 3. -1 and a -6, that's 5. It's distance, so they don't carry signs. Okay, there is no negative number. It's a distance between where I want and open the poles. If they are open of 0, then we put open of 0 there. Okay, so from this -1 to 2, that's 3. From -1 to -6, that's 5. So I'm going to stick 3 times 5 to the top. At the bottom, I got no open up 0s, therefore it's a 1. In this case, it gives me a value of 15. So 12, k, the control gain 12 will give me a stable system. But control gain of 15 will give me an even more stable system, maybe a slightly better performance as well, because now the pole is not here, it's not there, but it's at -1 point. Okay, so phase condition give us the tools to find the RootLocus. The gain condition give us a way to work out the control gain corresponding to different points on the RootLocus. So you need to find the RootLocus first, and then see where you want poles to be, and to find the control gain for that pole. Okay, some practical questions for you guys, and then you can actually try to sketch this. I think G1, G2, I want you to define focus on the real axis. Okay, identify different sections on the real axis and determine if each of the sections is on the RootLocus or not. G3, for that transfer function, I'd like you to actually sketch the RootLocus diagram indicating all the key points, the directions of pole movements, but also apply the gain condition to find the minimum value of k control gain. That makes closed system stable. That means make S to 0. Okay, close loop poles to 0. And for G4, this transfer function, I'd like you to draw the RootLocus diagram and then apply the gain condition to find the value of control gain that moves one of the closed poles to -3 point. Okay, so it's fairly similar to my examples. Okay, thank you.